Neyman-Pearson's test of acceptance implications. The second presentation expands an earlier introduction to Neyman-Pearson's tests with some further information about theoretical and philosophical considerations of using these tests. Here goes a snapshot before entering into any further details. Neyman-Pearson theory was put forward as an improved version of Fisher's test of significance, but it turned out to become a very different approach to testing research data. It provides good control over tests a priori and is more technical and deductive, but it also requires good knowledge of the populations of reference and the use of fixed parameters, and therefore it does not suit most research projects. Now, the first step is to set up the population effect size. Now, this is one of the main features of Neyman-Pearson's test, is that they refer to known population effect sizes. This implies that the hypotheses used for testing are always true, empirically speaking at least. We of course may expand this to also incorporate a theoretical hypothesis that is of assumed population parameters. For example, that a new treatment will have a large effect, even if never measured before. In this case, the truth of the hypothesis may be merely statistical. In both cases, however, the hypotheses are known or assumed to be true, and are not the one being tested. What is tested is the research data, not the hypothesis. Of course, research is done on samples taken from the overall population, and testing reduces to deciding which of two subpopulations they most probably pertain to. Now, these subpopulations are the distributions of our hypothesis, the main and alternative hypothesis, and the test decision ultimately depends on where the research data is located within such distributions. The second step is to select a test for maximum power. Now, Neyman-Pearson's main concern is to carry out research with good power, be this in the form of a type of test with good power, or by managing aspects of research design to increase power, for example by increasing sample size. The priority is to select tests or research designs that maximize power. Now, the most noticeable elements of a Neyman-Pearson's test are the existence of two explicit populations, therefore of two explicit hypotheses, both of which may explain the research data but with different probability, and both are treated as mutually exclusive for testing purposes. Therefore, the goal of the test is to decide which hypothesis explains the research data better. Because both hypotheses are plausible, the decision is a risky one, based on a trade-off between wrongly accepting one hypothesis or the other hypothesis. Furthermore, because both hypotheses are considered mutually exclusive, tests only need to be carried out using one hypothesis, pending that relevant information about the alternative hypothesis is incorporated into the test. So, the third step will be to set up this main hypothesis. Now, the main hypothesis is the one with more risk if rejected, so it's the one that you want to reject the least often. Such a risk, or type 1 error, is controlled by setting a small alpha level. Neyman-Pearson's tests are thus biased in favor of the main hypothesis, by making this type 1 error as small as possible. However, you cannot possibly know whether you make such error in any research project. Therefore, alpha is a long-run error probability. Now, alpha also cuts the continuum of effect sizes in two. So alpha actually doubles as a minimum effect size threshold as well, or minimum effect size. Yeah. So it cuts the effect sizes between those falling under the main hypothesis and those falling under the alternative hypothesis. So you can always consider that there is some proportion of the population effect size that will be taken as being explained by the main hypothesis. And this effectively reduces those effect sizes to be of little interest under the alternative hypothesis. Now, the first step will be to set up the alternative hypothesis. Now, again, consider the alternative hypothesis is such because it provides information to the test, even if the hypothesis itself is not being used. The information it provides is two: the effect size in the population, which as we saw is partitioned between the main hypothesis or minimum effect size and the effect sizes most probable under the alternative hypothesis, and therefore all potential effect sizes beyond the alpha threshold will be considered as more probable under the alternative hypothesis. And the second piece of information is the probability of making a type 2 error in the long run. The idea here is to reduce the probability of this error as much as possible once alpha has been set. Now here is the interesting thing. If the information provided by this hypothesis, the alternative hypothesis, is not taken into account when setting the test, then by default you are doing Fisher's tests of significance. Now the fifth step is to calculate sample size required for good power. Now for Neyman and Pearson, there is actually little justification in doing research with low power, because on the one hand the alternative hypothesis is rejected more often than it should, that is, the probability of making a type 2 error is too great, and on the other hand the main hypothesis cannot be reasonably accepted either, because there is still a sizable chance that is the alternative hypothesis that explains the research data. In such cases, of course, you ought to conclude that the research is inconclusive. Notice here that with Neyman-Pearson's tests, you can actually accept the main hypothesis if the research power is adequate. While in any case, you can always accept the alternative hypothesis even if power is low. Now the sixth step in the process is to calculate the critical value of the test. Now again, as we said before, the critical value of the test and the alpha level convey the same information when the test is set. So the alpha level is the theoretical p-value of the critical value in the particular distribution that we have decided to use for the test. Now, Neyman and Pearson prefer to use the critical value. And often is the good decision, because alpha is quite often confused with Fisher's p-values. Notice as well that all parameters coincide at the same point, the decision threshold. So this decision threshold is a fixed point in the distribution. So whether you use the critical value or you use alpha to make your comparison, this is a fixed point that shouldn't be altered. I mean, mucking around with one parameter will necessarily affect the other parameters. The seventh step is you carry on your research. And here, something to take into consideration is that the sample size used for the research should be close enough to the one recommended by the test for good power. I mean, it's reasonable to compensate for potential loss of subjects by increasing sample size slightly. But if the sample size differs substantially from that used to set the critical value, then the remaining parameters may also be affected substantially without you knowing it. And finally, decide which hypothesis to accept, which is just basically a deductive process based on where the research data fall in relation to the set decision threshold. So if the data fall under the alternative hypothesis, accept the alternative hypothesis. Otherwise, accept the main hypothesis, unless, of course, this main the research project itself has low power, in which case the research is inconclusive and largely a waste of resources. Last thing to take into account is Neyman-Pearson's tests are decision tests, not evidential. The p-value may be used instead of the critical value to compare the actual results, that is, to compare this p-value against the alpha level in order to decide between hypotheses. But once this decision has been achieved, the actual p-value is otherwise irrelevant. And basically, these are the main considerations to take into account when doing Neyman-Pearson's test of significance. Further references for helping to know more about this are just to provided here. And with that, we finish this introduction.